Hello everyone, welcome to section 6.3. This section we're going to talk about dealing with trig functions that have multiple angles in the argument. So we've looked at 6.1, which is fairly straightforward once you get the practice under your belt. There are a little bit of algebraic tricks, but nothing too serious. 6.2, we started bringing some of those double angle formulas, half angle formulas, things like that into the picture. We started using a bit more trig, but still relying on some algebraic techniques. In 6.3, we're going to see trig functions that have multiple angles involved, which means we're going to need to be really careful because those double angle formulas work great for when you have 2 theta, but what happens when you look at sine of 3 theta, or sine of 4 theta, or sine of 5 theta? So we don't want to keep relying on formulas that have very specific multiples inside the argument. We need a more general strategy. We need something that we can use in more situations than just double angles. So we want to look at trig functions with multiple angles. What I mean by that is, and probably the best way, is to start off with a nice example. And I actually pick number 5 out of the textbook, where it says find all solutions if theta is between 0 and 360 degrees, staying strictly less than 360 degrees, given the equation sine of 2 theta is equal to root 3 over 2. So now when we look at this, we might have the intuition to say, well, this is a double angle. My first attempt, I might try something like using that double angle formula to break this up into 2 sine of theta, cosine of theta on the left-hand side. But unfortunately, this is going to be a dead end. All right, the nice thing about having something where we just have multiples set equal to 0 is we can set each multiple equal to 0 and pick up a solution, but that's non-zero. Right? I can't say that sine of theta is root 3 over 2 because then I'd be multiplying root 3 over 2 by 2 and that's not even root 3 over 2 anymore. Right? So we can't just pick on a specific thing and say it equals this value. Everything on the left has to equal this value, not just one specific thing. We lose that zero product property. So this is going to lead us down a dead end pretty quickly, especially when we get to things like sine of 3 theta, sine of 4 theta, sine of 5 theta, right? Obviously, we don't even have formulas for those, so that's going to lead us nowhere. Rather, what we want to do is look at this in terms of the way we've been looking at it before, where this thing in the argument, sine of, in this case, I'll just call it some angle x. Right, this angle is just an angle. It must be spitting out this y value of root 3 over 2. So I can go to my unit circle and I can figure out where this angle, this argument, must be spitting out root 3 over 2 when I stuff that angle into the argument of the sine function. Well, since we're in degrees, we know where the y value is root 3 over 2 on our unit circle. When we look at the sine function, we're going to get 60 degrees. In quadrant 1, where it's positive root 3 over 2 for the y value, but it also happens in quadrant 2 at 120 degrees. Sine will be negative down here in quadrants 3 and 4, so obviously I don't want those. Sine's not negative. Now, this tells us that this angle must have been either 60 degrees or it could have been 120 degrees. Which is no different than saying that this angle to theta must have been 60 degrees or 120 degrees. All right, so that allows us to use the exact same technique we were using before, but now instead of saying x is 60 degrees, x is 120 degrees, what we're going to say is that 2 theta is 60 degrees. And 2 theta could be 120 degrees. All right, so now that's my angle is the red. It's 2 theta. It's more involved. It's not just theta. It's actually twice theta. Now, when we look at a trig function that has this multiple angle on the inside, remember that that's going to adjust the period of the trig function. This is going to oscillate twice as fast. Now sine, normally if I look at y equals sine of x, that function has a period of 0 to 2 pi. So when I look at y equals sine of x, I'll pick up some positives, some negatives, some negative, and I stop at 2 pi, or 360 degrees. But when I look at this function, and this is the function I need to solve, it oscillates twice as fast. So it's actually going to oscillate twice from 0 to 360. It's actually going to pick up some positive values, pick up some negative values, pick up some more positive values, pick up some more negative values. Right? So it actually oscillates twice as fast. So we're going to see it pick up 2 times as many solutions. But if I just divide this by 2, I get 30 degrees. If I just divide this by 2, I get 60 degrees. That's not all the solutions. We're missing some. So what we need to do at this point is look at the more general format for the answer. All right, remember we did some problems where it said find all solutions, period. Just all of them. Not between 0 and 360, all of them ever. And there's an infinite number of them. This is the format that we had to put it in, where k is an integer. And then what we would be doing is we'd be starting at 60 degrees, and then just traveling 360 degrees around the unit circle to pick up the next solution, and pick up the next solution, and pick up the next solution, and pick up the next, etc., etc. Same thing with the 120. We'd start there on our first trip around, pick up that next solution, we'd add 360 to it and keep that going, etc., etc. Okay, so far we've got twice theta should be 60 degrees plus 360 times some integer k. But I don't want to know what twice theta is. I want to solve for theta. I want to know what theta is. So I'm going to divide both sides by 2 to get theta. Could be, now when I have 2 terms, I have to divide each term by 2, 30 degrees plus 180 degrees k. Or for this second one, where it could have been 120 to start off, that would have given me a solution. I have to divide both sides by 2, which means I'll get theta could have been 60 degrees plus 180 degrees times k, again, where k is an integer. Okay, now this is every single solution for this equation has this format. But do I want every single solution? No, I want to be very specific and stay between 0 and 360 degrees. So what I need to do is look at this multiple and break this down onto a case-by-case basis. All right, so I'm going to look at the case where k equals 0. That means I'm looking at theta is equal to 30 degrees plus 180 degrees times 0. Well, that picks up my first solution of just 30 degrees. I also need to look at the case where theta could be 60 degrees plus 180 degrees times 0. I'm letting k be 0. Well, that just picks up 60 degrees. So here's some solutions, 30 degrees and 60 degrees. And so there's our first 2 solutions. But again, this function oscillates a lot faster than the normal sine function. So I'm going to pick up some more solutions when I look at the case where k equals 1. Meaning I'm looking at the case theta equals 30 degrees plus 180 degrees. Now I'm plugging in k equals 1. And I'm also looking at the case theta equals 60 degrees plus 180 times 1. So now I can add these 2 together. This will give me theta is equal to 210 degrees when I add 30 degrees and 180 degrees. And then I'll add these 2 together to get theta equals 240 degrees when I add 60 degrees plus 180 degrees. Here are all 4 solutions And you bet all four solutions are between 0 and 360. Now you notice this multiple is a 2. If I go to the case where k equals 2, I would plug in 2 times 180, that's 360. Well, and then I'd have to add 30. I've gone too far. So when you get to that multiple that you see here, you don't need to do that case. You stop at that case. You only do the cases for the integers k that come before that multiple. So this was a 2 theta, so there was no need for me to go further and go to k equals 2. I would have already guaranteed I went past 360, and the goal is to not go past 360. So this tells us we have 4 solutions. If we plug theta in, we'll get twice theta, and then evaluate sine of twice theta and pick up this proper value, root 3 over 2. So you can see how this technique is a lot different than using a double angle formula, which again, in fact, the double angle formula, give it a try, it's not going to give you the right solution. Or you may get lucky and pick up a right solution, but guaranteed you're not going to get all of them. Because if you do it that way, there's no way you're going to pick up every single multiple of the angle you need. Now let's take a look at, basically, well, same thing. Let's find all solutions if we'll stick to between, theta is between 0 and 360 degrees. But let's take a look at cosine of 3 theta is equal to -1. All right, let's take a look at this. Okay, well now we definitely don't have a formula for 3 theta plugged into the cosine function. Right, we don't have a triple angle formula. We have some double angle formulas for cosine 2 theta, but we don't have a cosine 3 theta formula. And like I said, we don't want to always go out there. If I come across the next problem where it's cosine of 7 theta, I don't want to look for a formula that has 7 theta in it, right? I'll be looking for formulas for the rest of my life if I do it that way. Whereas instead, I just use the general technique, and it works out a little better and a lot faster. So this angle that's in here, when I plug it into the cosine function, it better be spitting out -1. We go look on our unit circle, and we find that ordered pair, -1, 0. Cosine is the x value. So that means this angle here, 3 theta, must be 180 degrees. And again, we're talking staying between 0 and 360. So this tells me that 3 theta, not theta, if theta is 180, then I'm doing 180 times 3. But this oscillates 3 times as fast, so I need to pick up those extra solutions. So I'm going to say that 3 theta, this angle, will pick up the -1 when 3 theta is 180 degrees, plus the general form means I'll pick it up again if I go around the unit circle the whole trip again and again and again. So unlike the last one, I only have this one angle to deal with. But again, I don't want to know what 3 theta is. I want to know what theta is. So I'm going to divide by 3 on both sides. Make sure you put this plus 360 degrees K first, then divide by 3. Otherwise, you run the risk of only dividing 180 by 3 and then adding on 360. But that's not how we're going to pick up the multiples. Watch what happens when we do 180 divided by 3, we'll get 60 degrees. Plus 360 degrees divided by 3 is 120 degrees. And again, when you divide something that has 2 terms in it, make sure you're dividing each term by that value, because it's a common denominator. So each term is getting divided by that denominator 3. Okay, so now we're in a situation where we have a triple angle, which means we need to look at the case where k equals 0, the case where k equals 1, and the case where k equals 2. I don't need k equals 3, because 3 times 120 is 360, and then I'd have to add more. I'd be going way too far. So I go one less than the multiple that I see. So this is the general format for the answer, but they don't want all the general answers. They want between 0 and 360. So theta is 60 degrees plus 120 times 0, so it's just 60 degrees. Or theta could be 60 degrees plus 120 degrees times 1. Okay, that means theta is 180 degrees. Again, notice, still in the proper spot. And of course, k equals 2. We're looking for theta equals 60 degrees plus 120 degrees times 2, which is 240 plus 60 is theta must be 300 degrees. Again, still less than 360, so we're good. So this gives us all the solutions that we can find for theta between 0 and 360 degrees. Again, remember what these functions do, right? They oscillate. In this case, this one, cosine of 3 theta, that is actually going to oscillate 3 times as fast as cosine of theta. So I'm picking up 3 times as many solutions as I normally would. Instead of just this one, I'm getting all these multiples, picking them up faster and faster and faster. So I erased a little bit of that heading there. Okay, so if we're staying between 0 and 360, you might have already noticed that wouldn't it be easier if we could just write the general form? We wouldn't have to do this case by case. What if the directions said find all degree solutions, period, all of them? There's an infinite number of them, please find them. Then yeah, we would get to stop right here. So it actually becomes easier. We don't have to do a case by case basis if they say find all solutions. So let's do one of those. It'll actually be saving us a step in the end, or maybe a couple steps depending on the cases that we have to encounter. Let's say we find an equation and it just says find all degree solutions. And we'll pick on a problem. Let's say cosine of 4 theta is equal to 0. Let's say we want to pick on this equation. Again, big multiple angle in there. So we want to go to our unit circle and find where would cosine of some angle spit out the number 0. Well, it would be here at 0, 1. Again, we're in degrees, so I'm going to say 90 degrees, since that's what we're concerned with, degrees. And down here at 0, -1 for our ordered pair, that's 270 degrees. So these are the two values that I want, but my function has 4 theta. So 4 theta must be 90 degrees, or 4 theta could be this 270 degrees. Now again, because this oscillates 4 times as fast, I'm going to pick up a lot more solutions than just these two. These two would be good if I was staring at cosine of theta equals 0, right? My job would be finished. But that's not just theta, that's 4 times theta. So I pick up a lot more solutions. Let's go find all those solutions. But the nice thing is we don't have to do it in a case-by-case basis. So again, we're not doing cosine of theta, we're doing cosine 4 theta. So let's tack on our plus 360 degrees K plus 360 degrees K. Now the nice thing about this is I can divide the top by 4 and get theta equals, okay, that's not the nicest angle, right? 22.5 degrees plus, okay, 360 at least divides by 4 nicely. So I would get an answer that's like this. So it's a half angle, not the prettiest, but it is what it is. And then same thing here. Cancel, cancel. Again, make sure you divide each of these terms by 4. So I'm going to get theta equals 67.5 degrees plus 90K. Well, look at that. What do you know? We're done. We don't have to do the case-by-case basis. They want all degree solutions, which all degree solutions are of this form, where K is an integer. All right, so we want to just pick up the solution when K is 0, when K is 1, when K is 2, when K is 3, when K is 4, when K is 5, when K is 6, and we can keep going because they're not limiting us between 0 and 360 degrees. They're saying all of them, ever. Even the negative one, even if K is -1, -2, -3. Now you're traversing clockwise around the unit circle and still picking up all those solutions. All right, so it actually becomes a little easier. We can omit that last step of doing the case-by-case basis. But if it was a case-by-case basis, I just want to be very clear that because this is 4 theta, we would need to do the case K equals 0, K equal 1, K equal 2, and K equal 3. And so, if necessary, notice we would have to stop at K equals 3. And so that's actually quite a bit of work that we're saving ourselves. Well, I guess we're not saving ourselves, the directions are saving us. So that's nice. Okay, so let's switch it up to radian. We did a few in degrees, but let's switch it up to radian. Let's say we want to find all radian solutions. And again, it's saying all of them. So it's actually the nicer case where we don't have to do K equals 0, K equals 1, K equals 2, etc. We'll just give them the general format and stop there. And let's say we have sine of 10x. I'm going to pick on a big multiple. We'll say we have sine of 10x, so we're solving for x, is equal to root 3 over 2. So this means that, again, the angle, yeah, I know, that one's pretty big, right? 10x. Oh boy, that thing oscillates really quickly. So this means when we go to our unit circle, we want to be able to find where sine of some angle spits out root 3 over 2, this time in radian. Sine is the y value, so it needs that height, and it's positive root 3 over 2. So it's up here at pi over 3. And here at 2 pi over 3, which tells me that 10x is going to be equal to pi over 3, or 10x, that angle could be this, spitting out 2 pi over 3 for us. Now I still want to pick up all these extra cases, right? I don't want to divide by 10 yet, because then I just get 2 answers. And there's like a whole bunch more answers that we need to pick up. But I don't want to mix up degrees and radian, so now I'm going to do plus 2 pi k. And I'm going to pick up this first solution, pi over 3, and then the general form says you have to go a full 2 pi to get back to that solution every time. Or if I have 2 pi over 3 is where I'm starting, then I need to add 2 pi to get back to all those multiples of 2 pi over 3 that do give me a solution. So again, I'm just, instead of writing 360 degrees times an integer k, I'm writing 2 pi times an integer k. But again, we're actually pretty lucky because we want all radian solutions, so we do want to keep them in this more general form, so that saves us from having to do the case-by-case basis. We would have to do k equals 0, k equal 1, k equal 2, ... all the way up to the case k equal 9. Yeah, that's a lot of work. And we'd have to do it for each one as well. So that saves us a ton of work to do. Really all we need to do is just divide out by this multiple of 10, which means I'm taking this whole expression and dividing by 10. I'm getting x is equal to, if I do pi over 3 divided by 10, that's pi over 30, plus if I do 2 pi k divided by 10, that's pi over 5k. Pi over 5 times k, so k is in the numerator. If I do it for the other one, divide out by 10, cancel, cancel, have to do it on the right-hand side, which means I need to do 2 pi divided by 3, and then divide that by 10, aka multiply by 1/10 the reciprocal. So I get 2 pi over 30, aka pi over 15. I'm going to reduce that. Plus, again, we just did that, pi over 5 times k. And if you want to, you could take it a step further and get a common denominator here. We all know how to do that. We don't need to fight with that. All right, let's take it for what it is and just leave it there. Those are the two types of formats for the solutions that we will find. All right, it's nice we don't have to do cases because, again, they ask for all. So that's a lot nicer for us. We can stop doing anything at this point. There's all the solutions. Okay, let's see. What do we got? Maybe one more, maybe two more. I don't want this video to be super long, but let's allow ourselves to pump up the difficulty a bit more. Let's say we look at, I'm just going to steal one out of the book here. Find all solutions. Oh, wait, let me say find all. Let's stick with radian, right? Find all radian solutions. We've done enough with those. We've done enough with those degrees. And let's say they give us this equation, sine of 2x times cosine of x plus cosine of 2x times sine of x is equal to 1/2. Let me put that right back there. So let's say they give us something like this. Now be careful because we've got some double angles. One of them's in the sine function, one of them's in the cosine function, oh boy. And then we've got these single angles, just x, x. There's a trick out there that we need. Actually, I'm glad I have this pulled up. There it is. So it'll be down there. Remember that sine of a plus b? That's sine of a times cosine of b plus cosine of a times sine of b. If we use that, then we can break this up a little bit different. We can look at this in terms of that nice formula here, sine of a. Well, let's omit the parentheses here. Sine of a cosine b plus cosine a sine of b. So this is the formula that we're going for, which simply lets us rewrite this as sine of a plus b. So remember that formula. I can now rewrite this where a is 2x and b is x. I can rewrite this equation as sine of a plus b is equal to 1/2. Again, not going to immediately see it the first time you do this problem, but keep in mind we do have those formulas, so if you are stuck, go to those formulas. Hopefully something springs up a red flag and it gets you to identify, oh, this is sine of a plus b. So I can just break it up. Well, not break it up, actually, I guess condense it back down into sine of a plus b. Well, 2x plus x is just 3x. Again, I don't have a triple angle formula, but we know how to handle these now, thanks to this section. I want my sine function of some angle to spit out positive 1/2, and we're in radian, and we want all of them. So I want in quadrant 1 and quadrant 2, where the sine function is going to be positive 1/2, that's pi over 6, and that's over here at 5 pi over 6. I go to 6 pi over 6, but back it up one for me, 5 pi over 6. So that means that this angle 3x must be spitting out, or I should say this angle 3x is pi over 6 plus 2 pi k, or this angle 3x could be 5 pi over 6 plus 2 pi k. Again, I'm doing plus 2 pi k, where k is an integer, because this is a triple angle. It's going to oscillate 3 times as fast. I'm going to pick up a lot more solutions. But at least the good news is we don't have to do the case-by-case basis. We'll do one more of those next with the case-by-case basis, but for now, we just want the format for all of them. So I do have to divide everything by 3. Now, when I'm dividing by 3, I'll get x is equal to, so pi over 6 divided by 3 is pi over 18. Again, think about pi over 6 multiplied by the reciprocal 1/3, plus this is just stuck 2 pi over 3k. Again, we could force a common denominator, but that's fine for us. Divide this by 3. So we're getting x equals 5 pi over 6 divided by 3 is 5 pi over 18. I'm actually multiplying the 6 and the 3 in the denominator. And again, we already saw this is 2 pi over 3. There's nothing we can do with that. And there are all of our solutions. Again, all of our solutions. So we can stop there. We don't need a case-by-case basis. Even if we did have to do a case-by-case basis, not too terrible, right? K equals 0, k equals 1, k equals 2, stop. But those are some nasty fractions, so we'll take it. So this is really like the whole, the crux of the problem here lies in, can we identify that sine of a plus b formula and use that formula to get it back into something that's a lot nicer to solve. And then, like I said, let's do one more where we do have to use the case-by-case k values. Just so we can get one more practice. We didn't do one like that with the radian. So let's say find all solutions if, we'll go back to theta instead of x, if theta is between 0 and 2 pi. And so we'll stick within the 0 to 2 pi. And let's pick on Let's pick on 2 times sine squared of 3 theta plus sine of 3 theta minus 1 equal to 0. I am actually pulling this out of number 45 in the textbook, but technically 45 asks for degrees and the directions. I just want to do one more radian, so I'm going to switch that back up. So again, we'll stick with radian between 0 and 2 pi. This has that quadratic feel, right? There's something being squared, there's something, and then there's a constant, and it's set equal to 0. So it almost has that ax squared plus bx plus c equals 0 quadratic feel to it. So we're going to try to factor this like we did in the previous sections. And we'll see that this factors nicely, but be careful. Again, you're looking for 2 sine squared of 3 theta. So when I break this down into 2 separate factors, I'm going to do 2 times sine 3 theta times sine 3 theta for the first times the first to get 2 times sine squared 3 theta. So that's how it breaks down. I need a negative 1 on the end, but I want a positive sine of 3 theta. And again, just because we haven't seen one in this section, remember when you're checking, it's just like you're working backwards here to just check your inner and your outer terms to make sure you've got 1 sine of 3 theta. Right, my first times my first, yeah, that's 2 sine squared 3 theta. Yeah, my last times my last is negative 1. Those are pretty easy to see, but this is what I want to guarantee. I want to guarantee that I've got the correct factors that give me the correct middle term. Right, if we get this wrong at this step, there's no point in moving forward. We're going to get our answers wrong as well. So that's why I like to do that nice little check there. So we're definitely golden. We're good. We know that 2 times sine of 3 theta minus 1 times the quantity sine of 3 theta plus 1, I'm just simply rewriting it, has to equal 0, which means when I multiply these two big factors together and get a result of 0, either this factor is 0 or this factor is 0. Notice what that does. It breaks it into two smaller problems. 2 sine of 3 theta minus 1 is 0, or sine of 3 theta plus 1 is 0. And both of these problems have this weird triple angle involved with them. So I solve each one separately. Add 1, divide by 2. I get sine of 3 theta has to be 1/2. Which means, again, I'm looking for this angle 3 theta to spit out 1/2 when I plug it into the sine function. So that tells me, and again, I'm in radian. I'm in quadrant 1 or quadrant 2. The sine value is going to be 1/2 at pi over 6. And over here at 5 pi over 6, we just saw that. But now I'm looking at 3 theta is pi over 6 plus 2 pi k, or 3 theta is 5 pi over 6 plus 2 pi k. All right, I want to make sure I pick up every single multiple here, which means now I'm looking at theta is going to be equal to, if I divide by 3 on both sides, we'll get pi over 18 plus 2 pi over 3 times k, where k is an integer. Or I'll get theta equals, again, divide by 3, I'll get 5 pi over 18 plus 2 pi over 3 times k. So I'm dividing out by this multiple of 3 on both sides. So these are the general forms. I'm just going to put a square around them. This is not the final answer because, again, we need to do the solutions between 0 and 2 pi. So we don't want theta to go past 2 pi. But let's get this down first. And then over here we'll do our cases k equals 0, k equals 1, and k equals 2. And yeah, we do have to go all the way up to k equals 2 because we've got sine 3 theta everywhere. So let's subtract 1 and solve sine 3 theta equals negative 1. Okay, this one's a little nicer for us because the sine function is going to be negative 1 all the way down here at 3 pi over 2. All right, sine is the y value, so I need negative 1 for my y value, which means 3 theta is 3 pi over 2, but we want all the multiples, and then we'll do our case by case, so I'm adding 2 pi k there, which means I divide by 3 to identify theta. It's going to have to be pi over 2. So if I divide 3 pi over 2 divided by 3, the 3's cancel. Plus 2 pi over 3 times k. And again, this is not the final answer, but I just want to show you. So we have 3 different forms, and for each one of those forms, I have to do k equals 0, k equal 1, k equal 2. K equals 0, k equal 1, k equal 2. K equals 0, k equal 1, k equal 2. for each one of those different forms, because I'm going to pick up quite a few answers. All right, so plug in k equals 0. Oh boy, those are easy cases, right? Pi over 18, 5 pi over 18, pi over 2, right? Those get picked up really, really quickly. So we're going to say that theta is equal to, now, just to save us some time, all the k equals 0 cases, pi over 18, 5 pi over 18. They don't have to be in order, that's fine. You can put them in order later if you like. And pi over 2. So there are all the cases for k equals 0. We could also get some cases when k equals 1. So when k equals 1, we'll get 2 pi over 3 plus pi over 18, common denominator, just to get through this. I'll multiply 6 top and bottom here to get 12 pi plus another pi is 13 pi over 18. Same thing here, if k is 1, I need 2 pi over 3 plus 5 pi over 18. Need a common denominator, so we can multiply top and bottom by 6 for 2 pi over 3 to get 12 pi over 18 plus 5 pi over 18 is 17 pi over 18. Same thing over here, case k equals 1. I need to combine these two, which means I need to get a common denominator. So when I look over here, I'll have 2 pi over 3. Oh, did I? Oh no, I saw it. Okay. Sorry, I thought I divided by the wrong thing over here. Right? We needed 3 pi over 2 and then divided by 3. So that's still pi over 2. Yeah, we're good. Sorry. All right, but let's finish this up. You can tell I'm at the point where I'm ready to finish this, right? Pi over 2 plus 2 pi over 3. So I need a common denominator of 6. That's 3 pi plus 4 pi. That's 7 pi over 6. There's k equal 1. And then in the last case where k equals 2, because we have a multiple of 3, we need to stop at k equals 2. So I'll get pi over 18 plus 2 pi over 3 times 2 is actually 4 pi over 3, but I still need to multiply top and bottom by 6 to get a common denominator. 4 times 6 is 24, plus another one is 25 pi over 18. Same thing here, case k equals 2. Write down 2 here, multiply to get 4 pi over 3 plus 5 pi over 18. I'll need to multiply top and bottom by 6 to get a common denominator of 18. So I've already got 4 times 6 is 24, plus 5 is 29 pi over 18. Okay, that's still less than 2 pi, right? You can go verify that, because 18 times 2 is 36. So 36 pi over 18 is 2 pi. So we're still good. We're still within our 0 to 2 pi. And then last but not least over here, I need to double this. That's 4 pi over 3, but I need a common denominator of 6, so that's 8 pi over 6 plus 3 pi over 6. That's 11 pi over 6. Whew. Did it, right? See how much extra work this takes? Right, to go fight and find every single angle there. Right, it takes a little bit of work. And again, we're good because actually 12 pi over 6 is 2 pi. So we're getting as close as possible to pick up every single last answer we possibly can. But we're still within that 2 pi, so we're good. And we don't want to do the next case because then we'd already be past 2 pi and we'd have gone too far. So that is trig functions with multiple angles. Again, just a slightly different technique than we've seen in 6.1 and 6.2 already. And then that 6.3 is where we're going to cut it off for the next exam. So, well, once you've reached the end of this video, you're basically ready to handle the study guide, do some practice homework problems, and then just study for the test. Right? Keep practicing more and more of these problems. There's There's a good amount on the study guide, but you really need to do more than what's on the study guide just to get that extra practice so that when you do get to the exam, you're not struggling through the exam. The more you expose yourself to practice early, the easier it gets so that when you get the exam, you can just kind of blow right through it. So if you have any questions, please let me know. Otherwise, I will end the video here before it gets way too long, and I will see you for Chapter 7.